Good morning, my name is Jasmine Ortiz, and today I will present on Johannes Kepler and his contribution to what we know now as modern science. Now, modern science wasn't always modern as the name suggests, although it can be hard to imagine with our current situation in science that religion and science could mix. Individuals such as Aristotle were able to make it happen. Aristotle's view of the heavens being reflected in what we know as space heavily influenced astronomy before it became, modern. His idea that the heavens revolved around us positioned us in the center of the solar system, making the idea of the geocentric model highly recognized. Now, the model wasn't perfect. We see how retrograde motion challenged its credibility. However, mathematicians and astronomers such as Astronomy were able to work with the geocentric model in order to align it with the retrograde motion. An example of this is the Ptolemaic model, in which it uses epicircles, which is essentially a planet orbiting Earth while doing small circles. This model was convincing, but as time went on, it became more and more inaccurate. Few individuals were up to the task of challenging the widely established geocentric model, but Copernicus essentially made the notion that perhaps the idea that Earth being the center of the solar system was incorrect. Copernicus introduced the heliocentric model, which essentially placed the sun at the center of the solar system. But why wasn't Copernicus' idea adopted despite having the correct placement? Well, Copernicus kept epicycles instead of ellipses, which we later learned to be the correct orbiting path of planets. He wasn't able to find evidence against epicycles, and in some part, the religious view that the heavens were perfect resulted in him believing that a perfect circular orbit was better, leaving his module inaccurate. Now, when it comes to Ptolemaic versus Copernicus, the Ptolemaic model was continued to be used because of its simplicity over Copernicus. When Copernicus places the sun at the center and moves Earth and the planets revolving around it, the epicycles that they make leaves a big complexity on that system. But astronomy did not always remain with the Ptolemaic model. So astronomy did evolve, but it evolved with a different individual, Johannes Kepler. As we will see later, Kepler regarded the heliocentric model to be a better notion than the geocentric model. In his model, though, he changed the epicycles for ellipses. This change allowed him to make accurate predictions to planetary motion. Before we get started on Kepler's contribution to modern astronomy, let's take a dive into his journey in astronomy itself. Now, Kepler's idea that the heliocentric model was a better notion than the geocentric model stemmed from his association to Michael Meslin. Meslin was Kepler's professor in college, who also regarded the heliocentric model to be a better system than the geocentric model. Essentially, this just means that he believed that the sun was the center of the solar system rather than the Earth. Kepler eventually picked up on this notion as well. During his time as a professor of mathematics, Kepler meddled in astronomy. One of his projects that he took was studying the 6 Copernicus planets, which include Mercury, Venus, Earth, Mars, Jupiter, and Saturn. But that was just the beginning for this astronomer. Kepler was hired by Tycho Brahe to help him analyze the observations that he was recording for planetary motion. It could be argued that Kepler's success was due to Tycho's data. A little background to who Tycho was. He was a pre-telescopic observer who recorded astonishingly precise observations of the positions of planets, stars, and the moon. Tycho's observatory was actually located on a small island, which was funded by the Crown. During his time alive, Tycho was very particular on how much data Kepler would have access to. Although Tycho did hire Kepler to analyze the mathematical portions of the observations that he was able to collect, it could be said that Tycho was afraid, or rather jealous, that Kepler would discover something and take the credit for it. So eventually, Kepler's success had to wait for a little bit. Kepler was able to inherit Tycho's observations after his death. Having these observations at hand, Kepler was able to study the motions of planets with the full data and make a conclusion. That being said, Kepler's conclusion was his 3 laws of planetary motion. But what role did Mars play in Kepler discovering his 3 laws of planetary motion? Well, Kepler didn't have to focus on every planet to analyze the observations that Tycho made. Matter of fact, Tycho might have encouraged Kepler to focus more on Mars, but during his time of observing the data from this planet, Kepler made 2 particular conclusions from it. Mars's orbit was not a perfect circular orbit, unlike commonly believed of the orbits of planets. Instead, he noticed that Mars took an elliptical orbit, which is essentially a circle with an eccentricity. This type of orbit led to his next conclusion. Mars would speed up closer to the Sun and slow down when further from it. He would later generalize these behaviors on other objects orbiting the Sun. In a way, we could say that Mars was a critical component of finding the first 2 laws of planetary motion. Kepler's 3 laws of planetary motion essentially explain how planets move in space and the rules that they tend to follow. A quick reference to Smith, whose article can be found in the reference page of this presentation. Kepler's 3 laws of planetary motion weren't always known as this together. But we will cover this later during this presentation when we talk about our dear Sir Isaac Newton. Instead, this article references to the first law as the law of ellipses, the second law as the law of equal areas, and the third law as the law of harmonies. These 3 laws were taken from Kepler's analysis of Tycho's data. He was able to revive the laws that are mostly accurate and correct, except for some exceptions in the solar system. As a matter of fact, we learned about these during one of our readings, and this was about comets. Comets do not tend to follow the typical elliptical orbit around the Sun as planets do. Our first law is the law of ellipses. Essentially, ellipses are circles with eccentricity. We actually learned this during one of our readings in which it actually establishes a circle as a special case of ellipses where its eccentricity is 0. The main components of an ellipsis is its semi-minor and its semi-major. Its semi-major is actually the line that we see on this slide, on the picture, that runs horizontally across. The semi-minor is the line that runs vertically. Now, unlike a circle, although ellipses do have focus points, they don't have only one. They have 2. A circle has 1, and ellipses has 2. When placed in perspective of our solar system and a planet revolving around the Sun, one of these focus points is the Sun itself. The other would be empty. This plays an important role for law number 2. Let's analyze Kepler's second law of planetary motion, the law of equal area. What does it mean when it says that the planet sweeps equal areas in equal time intervals? Let's take a look at the picture placed above. A representation of Earth is seen revolving around the Sun as it lays on one of the foci. The area near the Sun is wider than the area further from it. But if the area is wider on one side and shorter on the other, shouldn't the time it takes Earth to complete them differ? Not exactly. Earth in this scenario is constantly accelerating and deaccelerating as it orbits the Sun. So while the area is wider for area 1, Earth covers it at a fast speed. Inversely, although the area for area 2 is shorter, it covers it at a slower speed. When analyzed, the time for both areas is equal to each other. But why does the planet accelerate near the Sun and decelerate when further from it? Newton has the answer to that. But before we talk about Isaac Newton, we need to talk about Kepler's third law of harmonies. The image attached contains the formula derived from Tycho's observations that reads that the orbital period of a planet squared is proportional or related to the astronomical unit of a planet cubed. This law is closely related to the first and second law of planetary motion. In addition, this formula is extremely useful when analyzing either the orbital period or the astronomical units of a planet far from our Sun. As long as we are able to measure one of the elements in the formula, we would be able to determine the other through a mathematical process. If we ever need to measure one or the other, we always refer to, or there are always exceptions, but we tend to refer to the formula placed above. Moving on to Newton, Newton is the why to Kepler's 3 law of planetary motion. Kepler presented strong mathematical descriptions to astronomy on how planets revolved around the sun, but why they did it in an elliptical order was a mystery unto Isaac Newton. Studying Kepler's 3 laws, Newton found the why. The answer to this was gravity. The main component that kept planets from leaving its orbit is gravity. Although we know Kepler's 3 laws to be accurate, without evidence, his laws weren't always as evidential. Newton's explanation solidified them to the astronomical community, allowing them to be adopted. Newton's laws of gravity states that every object with mass attracts other objects with mass. In the case of Law 2 of Kepler, the closer the Earth got to the Sun, the greater the gravitational pull the Earth would feel from the Sun, allowing it to accelerate. But once it was further, the gravitational pull lessened, slowing down its speed. Newton's law of gravity proved all of Kepler's laws of planetary motion. In addition, Newton's law of gravitational attraction allows us to question if objects with mass attract each other, and the Sun isn't the only object around Earth, then do other planets attract Earth and vice versa? The answer is yes. That is why we could see some deviations from Kepler's mathematical predictions, when the gravitational pull of other planets remained unaccounted for. The first steps to Kepler's 3 laws of planetary motion did not even start with Kepler, but rather it started with the failure of the geocentrism model that Aristotle and Astronomy advocated for. From the failure of geocentrism, heliocentrism was able to rise under Copernicus, hinting Kepler towards modern science. With the precise data from Tycho Brahe, Kepler was able to make a mathematical description of the solar system and its planets. But it did not stop there. Kepler's laws influenced Isaac Newton to go a step further and find the why to our solar system.